We'll just wait for a couple of more minutes for everyone to join in, and then we'll begin the session.
ಸವಸ ಮಾಡಂಗೆ ಮೊಸರು ಮಧ್ಯಾಹ್ನ ಮಾತಾಡು ಹೌದಲ್ರಿ ಕೇಳಿದಂತ
Okay, let's begin. So, hello everyone, this is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So, we'll be meeting every Tuesday to go over the contents of the previous week to help you solve the assignment questions of the next week. So, today we'll be discussing the contents of week 1 and week 2 and any of the doubts that you have. Okay, so let's begin. So these are the same equations that I'd shown the last week. So these are the equations that we'll be predominantly using while solving the questions. And these are some of the important ones. Okay, so the first one is the lift equation, which describes the lift curve slope, lift curve equation. So it's the CL versus alpha graph, which is very familiar to all of us, where CL naught is the intercept and CL alpha or DCL by D alpha is the slope. So for a cambered airfoil, positively cambered airfoil, something like this. For a symmetrically cambered airfoil, CL naught is 0, and hence it will go through the origin. Okay, so CL naught is 0. Then CD equals CD naught plus KCL square. That's the drag polar, which gives you the coefficient of drag, the equation for that. then you have the thrust required for a cruise steady level flight, for cruise condition. What are the conditions in that? You have lift equal to weight. You have lift equal to weight and thrust equal to drag. These are the two conditions associated with cruise flight. From there, you derive your equation for velocity. How? You take lift equals half rho v square SCL and then substitute the term. So lift equal to weight, substitute that and then equate it, reframe the equation to find out V. In the same equation, instead of CL, if you plug in CL max, you get V stall. We discussed what stall was in the last class. So can anyone just recall it? What was stall? You can either type it in or unmute yourself and let me know. What do you remember by stall?
The angle of attack where the flow separates and there is fall in lift.
Yes, okay. Stalling is the condition where there is a boundary layer separation or the flow separation and there is no sufficient lift to balance the weight. Okay, so you're correct, absolutely right. Stall. So our aim is to increase the stalling angle as far as possible. And if this happens at CL max, so also increase CL max. What is CL max? It's the maximum value attained in the CL versus alpha. Similarly, increasing the stall angle also means that reducing the stall velocity. So this is what we aim to do. We want to reduce the stalling velocity and increase the stalling angle of attack. They're corresponding to each other, okay? Then, so this was a graph that I'd shown in the last class. There is a change here. Okay, this is wrong. Okay. So in the last class, we had only seen that a minimum thrust corresponds to maximum range and minimum power corresponds to maximum endurance. So there was some confusion regarding that. So I just added another line to clarify this. So when they, in questions and all of these, when they just say maximum range, it refers to the propeller driven aircraft. Okay. So when this minimum thrust or minimum drag and minimum power conditions were initially framed, we only had propeller driven aircrafts. And so they just directly mentioned maximum range corresponds to minimum thrust and maximum endurance corresponds to maximum power. But if with the invention of jet engines, we knew that there are other conditions that come into play. And so the jet engine's maximum endurance corresponds to minimum thrust. And what does the jet engine's maximum range correspond to? So you can tell me in terms of CL by CD or value of CL or anything. So for minimum thrust, propeller-driven aircraft gives you maximum range. Jet-driven aircraft gives you maximum endurance. It corresponds to the case where L by D is maximum or drag is minimum. So CL by CD is maximum. And in this case, your value of CD is, CL is under root CD naught by K. And when you substitute this value into the drag polar, you get CD equal to 2 CD naught. Okay. Similarly, for the minimum power condition for a propeller-driven aircraft, it gives you maximum endurance. It corresponds to the case where CL raised to 3 by 2 by CD is maximum. And the CL value for this case is under root of 3 CD naught by K. And when you substitute this value into the drag polar, you get 4 CD naught. Now, along similar lines, what for a jet engine, what condition gives you maximum range? It's not this. This is wrongly written. So this is wrong. For a jet engine, which condition gives you maximum range? This was discussed in the class. So if anybody can recall it and let me know.
CL is equal to under root CD naught by 3K.
Yes. CD naught by 3K. Yes, correct. So for jet engine, max range is CL equals under root CD naught by 3K. It corresponds to CL by CD, CL raised to 1 by 2 by CD max. Okay. So these are the conditions that we will be using throughout the series. So mostly it will be propeller driven aircraft. If not specifically mentioned, if it's not explicitly mentioned whether it's propeller or jet, you can assume that it's propeller driven aircraft, even in the questions or even in the lectures. When it's just said maximum range or maximum endurance, you relate it to the propeller driven aircrafts. Okay, so remember these conditions. Just the CL, CD, you can obviously plug into your drag polar and find out at any point. Just remember the CL conditions. All right. Yeah. So why do you think there is this difference in propeller and jet driven? Why is the almost reverse conditions? Why is there a difference? What is the main difference in the functioning of propeller and jet engine? Some things, that some difference in their operations or anything that you can think of. Just think about it. Why is it different? Minimum thrust, it corresponds to maximum range for propeller, but it corresponds to maximum endurance for the jet. Why is there this difference in their functionality? What is different? What's the difference between propeller driven aircraft and jet driven aircraft? Anything, just any points that you can think of. Their definition of SFC, okay. Shreyash says definition of SFC. Okay, that becomes a little more. Can you tell me something a little more basic? What is the difference in the definition of SFC? Since you brought that up, can you try and tell me? SFC is specific fuel consumption, and what is the difference in their definition with respect to propeller and jet? Okay, that's all right, but can you come up with something a little more basic? The basic functionality. Okay, so SFC, in propeller, power is important, and in jet, thrust is important. Why? Why do you think power is more important in propeller and jet thrust is more important? Yes, the engines are different, but how are the engines different? So how, okay, in propeller driven aircraft, how do you get this thrust or power? Shaft power in propeller. Okay. And in a jet? So when you say shaft power in propeller, how does it ensure that the aircraft is moving forward? Okay, yes, you're right. Power generated is shaft power in propeller, propeller driven aircraft, and in jet it is thrust driven. But how do you think their functionality is different in terms of operation? Okay, let's just go to the slide, we'll see. So a propeller driven aircraft, it moves a large amount of air very slowly to produce the necessary power or thrust. In a jet driven aircraft, it moves a small amount of air quickly. So this is the basic functionality difference. All of your points are also right, but I was just looking for this basic difference. So it moves propellers a large amount of air very slowly, a small amount of air very produces the required thrust or the power to make the airplane move, right? So what happens is that in the case of a propeller driven aircraft, its power remains almost constant throughout with the change in speed, okay? So it remains constant with change in speed. So what happens is that the thrust drops. When the power remains constant, the thrust drops. Your equation for power was PV. So when the power remains constant and the velocity is increasing, your thrust will drop, right? So this you can see this in the graphs here. So the power remains relatively constant at a particular altitude. All power, thrust, everything reduces with reduction in altitude. That is a given. But everything else, like if your altitude is same, density is same, then with increase in airspeed, your power remains almost constant. But because of that, your thrust reduces. Now, reverse is the case for a jet-driven aircraft. What happens there is that the thrust remains constant. And because of that, with increase, so if your same equation, if you take power equal to thrust into velocity and thrust remains constant, with increase in velocity, your power will increase, right? So that is this graph. You can see this increasing, correct? With increase in airspeed, your power is increasing, but the thrust remains constant. This basic or fundamental difference between the operationality of these two types of propulsion is what gives you this difference in conditions for maximum range and maximum endurance. Okay, so this is where the difference lies. Okay, let's move on. So something that Sora discussed was the wing airfoil considerations for a better aircraft or for you to design your aircraft. Okay, so these are some of the aerodynamic aspects. So let's look at it. CL alpha. We want CL alpha to be as high as possible. So if I have two airfoils, say one like this and one like this, say this is A and this is B, CL versus alpha. Which aircraft or which airfoil would you prefer for your flight? A or B? B, yes. So because it has a higher CL alpha. Why do we need a higher CL alpha? CL alpha is the slope. We need a higher CL alpha. So why do we need a higher CL alpha? For positive CM naught. Okay. So both these cases, both A and B have the same CM naught, right? So who is this? Yeah. So Prajwal has said it's for a positive CM naught. So both these cases, A and B have the same CM naught, right? This is CM naught. CM naught. Okay. No. So your CL alpha and CM naught, what is the relation? Okay, somebody has said to delay stall speed. How is the stall speed delayed? Yes, you're right to delay the stall speed, but how is it delayed? Because in this case, both of them have the same stall angle of attack, right? The stall angle of attack is here. So how is the stall speed delayed? Yes, so Shreyas says we need a higher CL alpha for generating more CL for increasing alpha. Correct. So that is one reason. Because for the same alpha, your A airfoil gives you lesser lift than B airfoil, correct? So that is one reason. But yes, delaying stall speed is also a correct answer. Can you try to explain that a little? Because according to this graph, the stall angle of attack for both the airfoils is the same. So how is the stall speed delayed? It's not delaying the stall speed, right? So what was the equation for stall? V stall. What was the equation? So Rajit says option C is correct. This is not a question. We're just discussing some parameters. Okay. So they are all correct. We require CL alpha. All of them are correct. We'll just go over it one by one. This is not a question. So just remember that. So someone said delaying the stall speed. So we're discussing that in terms of CL alpha. We are right now at this point. So how delaying the stall speed or reducing the stall speed? Which one is more desirable? We want to reduce the stalling velocity, right? Yes. Yes. So what was the equation for V stall? Yes,
Square root
minimum stall
2.
speed. What was the equation for minimum stall speed? Or stall, V stall. What was the equation for V stall? This was in the first slide.
Square root 2 loading, wing loading divided by
Sorry, I
rho
couldn't
into
hear you. Did someone say something?
Black Panther Data.
Okay, if you're answering here, please mute yourselves. Rajit,
Square root 2
yes, square root
2 wing load divided by
divided by rho CL max.
rho into
Correct?
CL max. Yes,
Yes. So for these two airfoils, A and B, which one has a higher CL max?
B.
B has a higher CL max, correct. So that is how you reduce your stall speed, because B has a higher CL max. Your V stall, stalling velocity for B airfoil is lesser than for A airfoil. All right. So these are the two reasons why CL alpha should be increased. First reason, for the same angle of attack, higher CL alpha gives you higher lift. Second reason, it reduces the stall speed. Okay, both necessary desirable conditions. Next, alpha stall, we just discussed we need to delay it as much as possible. So pick an airfoil that gives you a delayed alpha stall. So something like this or this. So in this case, again, we would prefer airfoil B because your stalling angle of attack is delayed, but the slope of B airfoil is less. So these are different conditions depending on your mission specific requirements. It's a trade-off between all of these conditions. Okay, so you have to design your or pick an airfoil which is suitable to your mission requirements. Next, CL max. We just discussed this. We want to increase the CL max to reduce the stalling speed. Correct? This is just, we discussed this in first point. So pick an airfoil. If you want to reduce your stall speed, pick an airfoil which has a higher CL max. Okay. Next condition is M critical. That's critical Mach number. Can anyone tell me what critical Mach number is?
The Mach number at which the air over the any part of the aircraft attains Mach number 1.
Yes. Okay. So critical Mach number, you're absolutely right. It's the Mach number at which at any point on the airfoil, the flow reaches Mach 1. Flow is sonic. Okay. So you're right. So we want this critical Mach number to be as high as possible, because when the flow becomes sonic or supersonic, there are some disruptions in the flow. It becomes unsteady and there is a lot of mixing of flows happening there, and there is boundary layer separation, and so it does not produce the desired lift. So we want to delay the occurrence of sonic or supersonic speeds across the airfoil as much as possible. So we want the critical Mach number to be as high as possible, right? To avoid any unsteady flows. Okay, so that was that point. Next, CMAC positive. Why do we want this? These are all just desirable traits. Okay, they're not mandatory, but these are the conditions, or these are the criteria that you may want to consider while selecting an airfoil. So CMAC, what is CMAC?
Moment about aerodynamic center.
Moment about aerodynamic center. Perfect. So if I have a positively cambered airfoil, this is my aerodynamic center. The moment here, CM. Okay, so the moment at the aerodynamic center, the coefficient of moment at aerodynamic center is CMAC. So why do we want this to be positive?
To obtain a positive trim angle.
Yes.
Angle
To
of
trim
attack.
the aircraft at a positive angle of attack. Correct. So your equation or the graph for CM versus alpha was something like this. So this is CM and this is alpha. So at this point, in this case, the trim angle of attack is this, right? Trim is when the pitching moment becomes 0. So here, this is a positive angle of attack at which you trim your aircraft. If I have another slope, because for stability, for longitudinal static stability, I had mentioned that the only condition required is that your slope is negative, right? So for both of these cases, that is A and B, for both of those cases, the slope is negative. So the aircraft is statically stable. In the longitudinal case, it is statically stable. So both of them can be selected, but we choose airfoil A because you're trimming at a positive angle of attack. In the case of B, this would be your trim angle of attack, which is the negative angle. This is not desirable. Okay, so that is why you want your CMAC to be positive. So for a positively cambered airfoil, is your CMAC a positive, negative, or 0? for this airfoil? Just think about it. I think we had discussed this last week. Just think about it. So where does this moment at the aerodynamic center come from? This MAC, CMAC. So there is a moment at the aerodynamic center, which we will now discuss whether it was positive, negative, or zero. Where does it come from?
The initial pressure distribution over there.
Okay, so pressure distribution. Okay, let's just discuss that. So you have something like this, and you have something like this, right? So it has this pressure distribution, and it amounts to a difference in the forces, which gives you a net lift, right? So there is a net lift and net drag. This is the net forces, net aerodynamic forces that are caused due to the pressure differences, correct? So this lift and drag, they're acting at which point? Considered to act at which point? So because of this pressure difference, you have this lift and drag. Why is there a moment? So this is your aerodynamic center. What is this point? The one where lift and drag are acting, the aerodynamic forces are
The
acting.
CG.
I didn't hear you. Can you repeat?
CG.
CG. Okay. It's not CG. It will be center of pressure. Right? So your lift and drag or the aerodynamic forces act at the center of pressure. Now this center of pressure keeps changing with angle of attack. It becomes inconvenient for us to perform analysis about such a point because it keeps changing with angle of attack. So what do? We transfer the forces to a point that is independent of angle of attack. Such a point is called aerodynamic center for the airfoil, right? So when we transfer these lift and drag forces to the aerodynamic center, it comes with a moment, correct?
Yes.
Yeah, so that is your CMAC. Moment at the aerodynamic center is because you transfer the forces from CP to AC. Now, can you tell me if the aerodynamic center, the moment at aerodynamic center is positive, negative, or zero for a positively cambered airfoil, the one that we've drawn here?
It's negative.
It's negative, yes. So can you tell me that we are using positively cambered airfoils for wings, right? So it has a negative CMAC. So what can be done to make it positive? We can obviously use a negatively cambered airfoil, but it will not produce the necessary lift. So how can you make CMAC positive? Overall CM, the equation for pitching moment is CM naught plus dCm by d alpha into alpha. This CM naught has to be positive. For that, what we do, we add a tail, and then you adjust the tail setting angle such that your CM naught becomes positive. But if you want your airfoil CMAC to be positive, instead of using a negatively cambered, have you learned some other ways? So how will
We
it
can use
become?
the reflex airfoil.
Yes, you use a reflex airfoil. Can you tell everyone what a reflex airfoil is?
It is actually cambered backwards at the tip.
Yes, perfect. So what he's trying to say is uh, something like this. Okay, I haven't drawn properly, but it has a upward camber towards the tail. So what happens is that your CP moves closer or in fact ahead of AC. So what happens is that if your CP becomes here, so lift and drag. Now when you transfer this lift and drag to your AC, it comes with a pitch up or a positive CM value, right? So that is how you make your CMAC positive. Okay. So now these were the aerodynamic characteristics that we want, aerodynamic criteria that we should be using while selecting the airfoil. So how do we change? How do airfoils change these aerodynamic criteria? They are using their geometric parameters. Some of them are nose radius, thickness to chord ratio. Can you name some others? How do you change the properties of an airfoil? Nose radius you can change, thickness to chord ratio you can change. What are some of the other geometric parameters that you can change such that their aerodynamic characteristics change? Any geometric parameters, however you define the airfoil.
Max camber.
Max camber, exactly. Max camber. Anything else? Any other geometric parameters? There are several. So you can look up the NACA series. You've studied that. So you can see the criteria or how they are defining those properties change the aerodynamic properties. Okay. So these are just some of the geometric parameters. Okay. Let's move on. Yeah. Okay. So there was, I think, a question in the forum. So I thought we'll address this. There was a question about how the velocity for minimum power and minimum drag, they're different. So velocity for minimum drag, or just write on the equation for velocity. You have V equals, just now we did this, to wing loading by rho CL. And for minimum drag, your CL is CL MD, which we have seen in the comparison slide. And for minimum power, your CL MP. Upon substituting those two and comparing it, we see this is the final relation that we get. Okay, so velocity for minimum power is related to velocity for minimum drag using this equation. That is how they are different. I just thought we should address this. Okay, let's move on. Okay, let's start with some questions. I hope it's clear. Okay. The linear representation drag polar of a propeller powered aircraft is given by this graph. From the above mentioned graph, what is the value of CD naught approximately? Try doing this. Very simple, right? So what was the equation for drag polar? CD equals
CD naught plus KCL square.
correct. Now they've asked you CD naught value approximately from the graph.
0.011.
0.011. So this is something like a straight line, right? And this is a straight line equation. When it's CD and CL square, you have a straight line equation. So this CD naught is nothing but the intercept. So intercept in this case is 0.011. Okay, so that's the right answer. What would the slope be? K. Just take any 2 points and let's find out the slope. Approximately. Take any 2 points and approximate slope. K is the slope, right? So this is the straight line equation, y equals mx. This is mx and this is c. So K is the slope. Can you just take any 2 points and find out the slope?
Zero point zero four one.
0.041. Which 2 points? Okay, I'll just take any 2 points and we'll try solving. We'll see if it matches, okay? So I'm going to take this point and this point. So that's 0.02 minus 0.011 by 0.2 minus 0. So let's just calculate this quickly. So something around 0.045, something around this, right? So that is the approximate value, correct? Yes, so the next question was to find out K. So we've just done that. So when they give you such equations, just equate it to a straight line equation, intercept, slope, and take any 2 points and find out the slope. Okay, is everyone else clear with how we did this? It's fairly simple, right? It's a straight line equation. You're approximating the points to a straight line and trying to find out. Is everyone clear with that? Okay, let's move on. For the same graph, they've given you CL alpha as 0.098 per degrees, and they've given you alpha at 0 lift to be -1 degrees. Then they've asked you to find out the angle of attack for maximum range condition. Can you try doing this? We'll solve this together, but take a few minutes and try doing this. They're giving you CL alpha and angle of attack at 0 lift. For maximum range condition, remember that, okay? So start with that. So CL for maximum range. This has already mentioned that it's a propeller powered aircraft. So maximum range for a propeller driven aircraft, CL. What is the value? Start there and try solving it. What was the CL max range? CL equation for max range for propeller driven aircraft?
CD naught by K.
CD naught by K. Under root CD naught by K, right?
Yeah.
Okay, so now we have the value of CD naught. What was it? 0.011. So that's 0.011. K was 0.045. Under root that, what would this value be? I haven't calculated it, so let's try doing it now. It's around 0.49, something like that. So that is your CL for maximum range. Now they've asked you to find out angle of attack corresponding to this. How do you do this?
CL is equal to CL alpha into alpha.
CL equal to CL naught plus CL alpha into alpha, right? There's a CL naught also.
Yeah.
Yes. Okay. So now we know CL alpha is given in the question. This is what we have to find out. So before that, we need to know what is CL naught. How do you find CL naught? How do you find CL naught? I think we've done a similar question last week. How do you find CL naught? How do
At
you find? Yes, tell me.
0 lift angle of attack minus 1.
Yes, so you have your lift curve slope is something like this. You need to find CL naught. And this is -1. You need to find CL naught. You have CL alpha. So CL naught is nothing but CL alpha is 0.098 into 1. So in this case, it's just 0.098. That is your CL naught. Plug it in here. You have 0.49, 0.098 plus 0.098 into alpha. alpha is 0.49 minus 0.098 by 0.098. So what is this value?
Ma'am, shouldn't it be minus 0.09?
Which one? CL naught?
Yeah.
This is a positive quantity, right? So you just have to take the magnitude of this. So it's just the magnitude into the slope. So CL naught in this graph is it's positive, right? CL naught will
Okay.
either be 0 or positive. It will not be negative, right? For an airfoil.
Okay.
So you can, let's just try doing this. If I take these 2 points, this is 0.1, this is 0.2, and I find the slope. So CL alpha is the slope, right? Is CL naught minus 0, correct? And you have 0 minus of minus 1 is 0.098, correct? So now when you substitute, you will get CL naught is nothing but 0.098 into 1. I hope that's clear.
Yes.
Okay, yeah. So now what was the value for angle of attack? That was our question. So this one, this value,
4 degrees.
4 degree. Okay. So that is the value. That is the angle of attack corresponding to maximum range of this propeller driven aircraft. Yeah. Yeah, so these are the formula that we used. I just put it there. Next, same question for a maximum power condition. Try doing this. It's just very simple. Just try doing it. We had done it for the maximum range condition. Here they've taken it for the maximum power condition for a propeller driven aircraft. The same, all the other data remains same, just compute it for the maximum power condition. .6 degrees. Is anybody else getting any other answer? Okay, let's just try doing this. So the only difference would be in the CL value. Everything else is same. So CL for maximum power. What was the value for a propeller driven aircraft? Can someone tell me?
Under root 3 CD naught by K.
Yes. Under note 3 CD naught by K. And your value for CD naught was 0.011. K was 0.45. So you get some quantity there, right? And that would be the only difference. The rest of the things will remain same. So CL is CL naught plus CL alpha into alpha. CL would be this new quantity, which is, can you tell me the value? 0.885. So it will be 0.85 is 0.098 plus 0.098 into alpha. And so alpha would be 0.85 minus 0.098 by 0.098. And so you get something around 7.6 degrees. Okay, did everybody get this? Or did someone get a different answer? Or did everybody follow this?
Ma'am, what is the CL for minimum power?
CL for minimum power. Okay, this should have been minimum power. Question should have been minimum power. Yes, that's right. Should have been minimum power. It's not max. Our condition is minimum thrust and minimum power, right? That was a mistake in the question. It should have been minimum power. Thanks for pointing that out. It should have been minimum power. Okay. Let's go back to those conditions. So here it's minimum power and minimum thrust required. So not maximum power. That was a mistake in the question. It should have been either maximum endurance or should have been minimum power. Okay, that was a mistake in the question. Okay. Apart from that, is this question clear? Okay, I think we'll move on. Okay. So yeah, these are the conditions that we used. Again, it's minimum power. Minimum. Okay. Moving on. Next question. If the leading edge of the wing is extended during takeoff, how is stall angle affected? Think about this for a minute. Increases. Okay, can you explain? So Shreyash says it increases. Stall angle of attack is increased. Yes. So due to more attached flow, correct. So if your airfoil and if your leading edge is somehow extended, your flow remains attached for a longer duration. So you have a wider range of angle of attack to vary it before it achieves stall, right? So you have more attached flow or more time or more alpha range for which the flow is attached. And so you have increased stall angle of attack. So what such devices do you know? These are called high lift devices. Can you name some? We will be going over this during the course of this lecture series. Can you name flaps? Okay.
Flat.
Okay. Yes, flaps are high lift devices. Anything that extends the leading edge, are you aware of?
Flats.
Slats.
Slats and slots, all of them, correct. So we will be discussing this during this course. So these are some high lift devices, okay? So they increase the lift during takeoff and landing, or they are deployed in such conditions. Here, in this case, it will maintain the attached flow for a longer alpha range. And hence it increases the angle. So answer is increases. Correct. Next, I think we had a similar question last week. For the jet-powered civilian aircraft, the thrust-to-weight ratio in climb flight will be. So begin with the climb equation and then try to find out. So free body diagram for climb. This is thrust, this is drag, lift, mass, and this is, what is this angle? This angle, what is this angle?
Alpha.
Flight path or climb angle represented by gamma. Okay, so try to write down the equations for this free body and then come up with thrust to weight ratio of jet powered civilian aircraft. So what are the equations of motion? Can we start? Let's start with thrust minus drag minus W sine alpha, unaccelerated flight, so steady flight, so it will be 0. Then you have lift minus W cos gamma equals 0. Correct? Am I missing out something? Okay, so we don't need this second equation. Just take the first equation and try to find out thrust to weight ratio. Just take this equation. What is the equation for thrust to weight ratio? Just equate thrust equal to something equal to, rearrange the equation, divide throughout by weight. So it's just T equals D plus W sine gamma. Thrust to weight ratio is D by W plus sine gamma. So from this, can you tell me? You can just rewrite this approximately equal to 1 by L by D, because L by D only comes when it's for the cruise. So L equal to W if you consider that. Okay, so it's only approximately equal plus sine gamma. Now L by D is typically around the range of 10, 15 like that. So you have, this will be less than 1. What about sine gamma? It will also be less than 1 because it is, it's less than 90, right? Gamma will never be 90. So for a civilian aircraft, your gamma is very, very small. Why does it have to be very small for civilian aircraft?
For
The
the
climb angle.
stable flight, for the care of passenger or something.
Yes, so for the comfort of the passenger, you cannot have very high climb angles throughout the course of the flight. You cannot have gamma that's very high. In fact, it's very, very small. So gamma, this is an assumption that we make for civilian aircraft, which is true. Gamma will be very, very small, very less than 1, or it's very small, right? So the sine gamma value is again very minuscule. It's less than 1. So this overall term, thrust to weight ratio, will be less than 1. Generally, it will be less than 1. Okay, so the value is less than 1. Okay. For fighter aircrafts, you will have higher values. You will have, in fact, 90 or greater than that. That's a different case. But here we're doing civilian aircrafts. So less, the assumption or the condition that you should remember is that your gamma, flight path angle, your climb angle is very, very small. Okay. Next question. An aircraft has a wing area of 23.69 meters square and weight of 4,535.93 kgs and a clean drag polar of, the equation is given, CD equal to CD naught plus KCL squared. They've given you aspect ratio and efficiency factor. Calculate L by D max. How will we go about doing this? Try doing this and then we'll solve it together. How will we proceed with this question? So L by D max, they've asked you. L by D max can also be CL by CD max. So L by D max is equal to CL by CD max. Okay, this is the hint. Try doing it now. You just have to find the ratio. 12.16. Can you tell us how you did it? Can you take us through your steps? Okay, is anybody else getting a similar or different answer or anything?
I just did the CL equal to under root CD naught by K.
Okay.
Then I divided it by that drag polar. CD equals to 2 into CD naught.
Correct. Perfect. So he has taken CL equal to CD naught under root CD naught upon K, which is the value for CL that corresponds to L by D max, or minimum drag or minimum thrust required. Okay. So CD naught is 0.023 and K is the slope. So you have 0.023 upon K is 0.0735. You get a value and 0.55. Similarly, CD for the case of L by D max is 2 CD naught. Or you can just directly substitute it into your drag polar and you get the value either way. Either way, you get the same value, okay? So for the L by D max or minimum drag or minimum thrust required case, it's also equal to 2 CD naught. Okay, so just substitute it. 2 into 0.023, you get 0.046 and just take the ratio. So this is for L by D max, L by D max. So the ratio CL by CD max gives you 0.55 by 0.046, which is the answer that Shreyash has got. It's 12.16. So it's this one. Okay. The next question. Okay, so these are the equations that we have used to find out the L by D max. I've just put it up in the slide. Let's go to the next question. CL at minimum drag. We just computed this, right? So CL at minimum drag, it's just CL is under root CD naught upon K, which we just calculated to be 0.55, so 0.56, this is the one. What is the CL at minimum power? What would the value be, or what would the equation be? CL at minimum power, CL for minimum power condition.
Under root 3 CD naught by K.
Yes. Under root 3 CD naught by K. So these are the ones that you need to remember that will be used throughout these questions. Okay, let's go on to the next question. Yeah, so this is the equation that we used. Then calculate velocity at minimum drag. Again, fairly simple. So direct substitution. What was the equation for velocity? Just general equation for velocity.
Root 2 W by S upon rho CL.
Yes, 2W upon rho CL. So for the minimum drag condition, you just have to use the CL for minimum drag. That's all. That's the only difference. And the data is given in the previous question, okay? So if you wanted the data, just try doing it. So you have W, you have S, density at sea level, you know, and the CL you've calculated. $74 meters per second. Is anyone else getting the same answer? Let's just do it. So it's under root 2 W upon SW was 4535. Into 9.81. Then you have, there was an S there, so that is 23.42, 23.69. 23.69. Density is 1.225. CL minimum drag was 0.56. And when you substitute all this, is everybody getting 74? Yeah, so 74. 74.04 meters per second. So that is the right answer. Okay, let's look at the next question. Yeah, this is the formula that we used. What is the value of minimum drag in newtons? By doing this? Can all of you mute yourselves if you're not asking questions or answering them? Person logged in as Zoom user, can you please mute yourself? Person logged in as Zoom user, can you please mute yourself? Let's focus on the question. How do you find out the minimum drag? How do you find out the drag? Okay, 3659.09. Please guide us through what you've done. How did you find it out? Drag d min. How did you do it?
Half rho v square
SCD and both
SCD.
minimum drag conditions. Let's just do it. So it's half 1.225. Velocity was 74.04. Area was 23.69. And CD at minimum drag was 2 into 0.023, right? 23. So if you solve this, you get 3659.09. 59.09. I hope everyone's getting the same answer. Let me know if you are getting different answers or if you have any doubt. Is the series of questions clear to everyone? Okay, if not, we can get back to it, but do ask me, okay? Okay. Yeah, so this is the equation that we used. It won't be a drag equation, but just substitute the minimum drag condition. So velocity at minimum drag, CD at minimum drag. Similarly, if they had asked you for minimum power, find the velocity at minimum power, find the CD at minimum power. You know the formula for both. Okay, now look at this question. Figure 1 gives the plot between power required and velocity. So what does point A represent? Very simple. First question, what does point A represent? It's very simple, right? Point A.
Minimum power required.
Exactly. Minimum power required. So next question, what does point B represent? Look at the graph and what does point B represent? Think about it. They have given you a hint in this. That is a hint. Using that, can you tell me what does point B represent? Minimum thrust required. Okay, how is it minimum thrust required? So in the options, it would be if minimum thrust required is the right answer, then options it would be from the given options. The fourth one, correct. So point B, according to him, minimum thrust required would be CL by CD maximum. Correct. How would you, how is it the minimum thrust required? Can you try explaining? Thrust required equal to drag. Okay. So the point which has, he's right. So here the slope for the lines, right? Constant slope lines. If I were to draw constant slope lines throughout, the line has to intersect the graph, and the line with the least slope or the least drag gives you the minimum thrust required. Correct? So this is the line. This is the constant slope line that gives you the minimum thrust required or minimum slope. Correct? This will be theta minimum. All the other thetas will be greater. And if it's less than this theta minimum, the line does not intersect with the graph. So the line, the constant slope line, which intersects with the graph with the least slope, gives you the minimum thrust required or gives you the minimum slope, right? So that corresponds to CL by CD maximum. So this is point B and this is point A. That is the right answer. Okay. Okay. Let's move on. Yeah, so this is how you came up with that. So that point A, this was A and this is B. Point A corresponds to the minimum power required. Point B corresponds to minimum thrust required. And this is how we arrived at it. Okay. Next, an aircraft has a gross weight of 2,700 kgs. At the end of the mission segment, it has a weight fraction as 0.85. Determine the fuel consumed during this mission. How will we do this? Again, try doing it and then we'll do this together. Okay.
$405.
Okay, how did you get to that?
That's the 15% of the weight.
Percent of the weight. Okay, so you can just do it by if taking weight fractions, you can take gross weight W naught minus the weight of fuel by W naught equals 0.85, correct? Weight final. This is not what is given. Let me just erase this. So W2 or the final mass is weight of the fuel by initial weight. So you have this weight of the fuel. They've given you the weight fraction at the end of the segment. So you have W2 by W naught. So W2 by W naught is 0.85, and they've asked you to find the weight of fuel consumed. So if you just simplify this, you get 1 minus 0.85 is weight of the fuel by gross weight, which is 2,700, which is 15% of the final of the gross weight. So weight of the fuel is 2700, 1 minus 0.85. You get 405 kgs. Is everyone else clear with this? Okay, let's move on. Next question, more simple question along the similar lines. An airliner with a takeoff gross weight of 5,100 kgs is cruising with a fuel weight fraction of 0.28. Then what will be the weight of the fuel in kg? Very simple. Very simple, right? So you just have to do weight of fuel by gross weight is 0.28. So weight of fuel is 0.28 into 5100. What is this value? 1428. Okay. So that is the weight of fuel. Very simple. Now look at this question where we will be using concepts like weight fraction, mass fraction. Just read the question. So the total weight of the fixed wing aircraft is given by weight takeoff is given by weight of the avionics, weight of the various other subsystems, weight of the propulsion device, propeller, whatever propulsion system, the other miscellaneous weights, weight of the structure, weight of the payload, and weight of the fuel. Okay, so they've described what each quantity is, weight of structure, weight of subsystems, and all of those. The fixed wing propeller powered aircraft has the following characteristics. Mass fraction of the structure is given to you, 0.23. Then they've given you mass fraction of the subsystems as 0.05. They've given you power to weight ratio, 0.14 HP per kg. BSFC is 0.6 kg per kilowatt hour. They're giving you mass fraction of the propulsion system, or propulsion unit, 0.08. Then they've given you L by D max, the ratio of L by D for minimum drag or minimum thrust required. They've given you cruise airspeed, 55 meters per second. They've given you CL trim. They've given you propeller efficiency. Maximum range of the aircraft is given as 1,000 kilometers. And wing area is given as 6 meters square. Okay. And they're giving you the weight of avionics, payloads, and other miscellaneous weights to be 60 kgs. Okay. So now look at the question. The value of fuel mass fraction is. Try doing this by yourself and we'll do this. Just go through what all are given to you in the question and what is asked to you. Just read it carefully and maybe come up with an idea of how to solve it, and then we'll solve it together. They've given you the maximum range of the aircraft. They've told you it's a propeller powered aircraft and they've given you maximum range. So start there. What was the range equation? Start there. Try doing that now. What was the range equation for propeller powered aircraft? So it was propeller efficiency by SFC, right? So SFC was represented by C. You have CL by CD or L by D max. Same ratio. And then you have ln initial by final. Okay. Try starting at this equation. Try reaching the fuel mass fraction. And try to find out the steps. This was the maximum range equation, right? So, which is given to you. You have R max, you have propeller efficiency, yes. You have C, SFC is given, right? So they've given you, yes, that is there. They've given you L by D max, that is there. And then you have, yeah, so then how do you proceed with this? R max is given, yeah, that is also there. How will you proceed with this? Please check the value of the specific fuel consumption, what is given and what is needed. So C, what was the unit of C that sir had used? What is the traditional unit that we use in this equation? What is the unit? It should be Newton per watt second, right? So convert it to that unit and try doing this. What is given is kg per kilowatt hour. We need it in Newton per watt second. How do you convert it? You take 0.6 into 9.81 kilowatt, make it watt, and hour, make it second. That's all. Try doing it now. Just plug in the values, right? So R max is 1000 kilometers, right? 1000 kilometers. So it should be in meters again. So 1000 into 10 raised to 3. Propeller efficiency is 0.65. Your SFC is, what is the value of this? Okay, let's find out that. CL, please mute yourself. Zoom user, please mute yourself. L by D max ratio is 11. And then you have initial upon final. So what is this value? Just compute it and find out and let me know the C value. SFC. (1.63 into 10 raised to minus 6 Newton watt second. So I just plug that in here. 1.63 into 10 raised to minus 6. So ln Wi W final is, what is the value? I haven't calculated it, so let me just try to 0.65. I'm getting 0.22228. Right? Is everybody getting this? Please let me know if I'm I'm making any mistakes. So I've got 0.228. So your Wi by W final is e raised to 0.228, which is 1.256. Correct? Let me know if I'm making any mistakes, okay? And then what we need to find is fuel mass fraction. So if I expand this, so it is Wi. Okay, let me just flip it, okay? So if I write W final by Wi, I get 1 by 1.256, correct? And how do I write W final? W initial minus weight of fuel by W initial is 1 by 1.256. Let me just draw this line here. So what happens is 1 minus W fuel by W initial gives you 1 by 1.256. And what we need to find is W fuel by W initial, which is 1 minus 1 by 1.256, which is, what is the value? Point 0.2, correct. So 0.2, this is the final answer. So is this process clear? What we did? So you start range equation, substitute all the terms by noting that C, the specific fuel consumption, the unit should be Newton per watt second. What is given to you was kg per kilowatt hour. You convert that into Newton per watt second, plug it into the equation. You have L by D max ratio is given in the question. Put that into the equation, find out the ratio Wi by W final, and just manipulate it by taking its reciprocal. And then you take one, so it becomes W final by W initial. And then you split, you rewrite it such that your weight of fuel comes into play. What is weight of fuel? Initial minus, or final is initial minus fuel, right? So just put that into that W final equation, and then you can find the ratio W fuel by W initial. Okay, this is how you compute all of these weight fractions. Okay, let's go to the next question. The weight of the aircraft in kg will be. How do we go about doing this? Start with the first equation, this one. Start with that and try finding it out. Weight of the aircraft. Weight of the aircraft. So they basically asked you to find W takeoff. That is the question. How do you find this? I've asked you the W takeoff. So that equation is given to you. Try manipulating the terms of that equation here to get the quantities that are already given to you in the question. How will we do this? So let's try doing it. So I write down that first equation. You take off equals W avionics, W sub plus propulsion system, W other plus W structure plus payload plus weight of fuel. Now avionics, payloads and others are given to you directly. So that is avionic, payload and other, it's given to you directly. So you have, that is 60. That's 60 plus weight of subsystem plus weight of propellers plus weight of structure plus weight of fuel. Right? So this is given to you. Now manipulate the equation such that you can get this value. So leave 60 here, take all the other terms on the other side. So you have WTO plus minus W subsystem of minus W structure minus W fuel equals 60. Can you do it from here? How do we proceed? How do we proceed? Take W takeoff common. So you have W takeoff. So it becomes 1 by W subsystem by W takeoff minus W prop by W takeoff minus W structure by W takeoff minus W fuel by W takeoff equals 60. Now, subsystem by subsystem weight fraction, do you have it? Yes, you have it here. Propellant weight fraction, propeller, this one, yeah. Structure, you have it. Weight of fuel, weight fraction of fuel, we just computed it, right? So you have all of these quantities. So just substitute it in there. 1 minus subsystem 0.05, propeller 0.08, structure 0.23, fuel we just calculated 0.2 is equal to 60. Now the only unknown is takeoff weight. So it's 60 by this quantity. So what is the final answer? 136.36, correct. So it's around 137 kgs. Approximately equal to 137 kgs. Okay. So this is how you go about doing such questions. Okay, when they've given you the weight fractions, try dividing the entire equation by the takeoff weight and then just substitute the fractions, the ratios. All right. Okay. Next question. What is the weight of power plant in kgs? This should be simple, right? Now that you have the takeoff weight and you have the mass fraction, it should be very simple. Very simple now. How do you do this? Weight of the power plant. So, oops. So, what is the mass fraction? It was 0.08. So, it's W. Power plant is the propeller here, okay? So, W takeoff is 0.08. Weight of propeller is 0.08 into 137. How much is this value? How much is this value? 10.9. So that is the weight of the power plant. Similarly, you can find the weight of any of those components because you have the mass fractions. Just multiply it with the takeoff weight and then you get the mass estimates of each of those quantities. So you can do it for structure, you can do it for the subsystems, right? You can fuel, obviously you can just multiply it, weight of fuel, where you have the mass fraction of the fuel, just multiply it with the takeoff weight and you get the mass of the fuel required. Next, what is the peak power required? Maximum power, peak power that will be required during the course of this flight. What is the equation for power? So you have, they've given you P by W, right? P by W is given. Correct? So P by W is 0.14 and they've asked you in HP, so there's no need to convert it. So this is 0.14. You need peak power is 0.14 into what weight? This W, what weight should we take for peak power? What will be the maximum power required? Peak power. So what weight should we take for that?
Of
What
it.
takeoff weight, exactly. So just multiply with the takeoff weight, that will be the peak power required in HP. So just multiply it, it's 137. So 0.14 to 137, what is the value?
$19.80.
So that is your peak power required. Okay, very simple. Next, what will be the value of trim speed? V trim. V trim. That is what they've asked you to find out. Look at what is given to you in the questions and then try solving this. So what was the equation for any regular velocity? Under root 2W by S by rho CL, correct? For trim, you'll just have to replace with trim values. So trim CL, trim, trim, which is given to you in the question, right? CL trim is given. So 2 into 137 into 9.81. S wing area is 6. Density 1.225. And CL trim is 0.3 under root of this. So what will the value be?
35.
35, right?
Yes.
35. 35 meters per second. So that is the trim velocity. Okay. Now let's move on to the next question. Yeah. So this is for a certain angle of attack at a given altitude, the lift will be doubled for which combinations of S and V? How will we go about doing this? I hope the previous question, the series of questions was clear to everyone. If there's any doubt, do stop me and do ask me. Okay, so yeah, let's get back to this question. For a certain angle of attack at a given altitude, the lift will be doubled for which combinations of S and V?
D.
Sorry?
D. Fourth.
D. Is D the only option?
C.
Okay, so to do it in a systematical manner, let's just write down the equation for lift. They've asked you lift will be doubled, so just write the equation for lift. That's half rho V square S CL. Now the things that are constant, we'll just group them together under A. So half rho and CL, these are constant, right? So A V square S, correct? So just group them together. So let's just do it for the first case. L1 is A, and you have root 2 square V square S. What is the value? 2A V square S. For second lift, you have A half square V square and 2S. What is the quantity here? You have A V square S, correct? Yes, by 2 in fact, okay. L3 would be A V square 2S. So here you have 2A V square S. And L4 is A 2 square V square S by 2. Again, you have 2A V square S. So A, C, and D, all three give you double, right? All three cases, you have doubled the lift. So when such questions are asked, please check all the options. If you find one, don't stop with that. Just check all the cases. Okay, so there may be more than one correct answer. Okay, so just try out all the cases. Okay, next question. Yeah, so this was the equation that we used to find out the lift. It's very familiar to all of us. We just substitute it and just compare the lifts. Okay, next question. The drag polar of an aircraft is given by CD is 0.02 plus 0.19 CL square. Again, so this is CD naught plus KCL square. What are the values of parasite drag coefficient and coefficient of lift when the aircraft is operating at maximum L by D? What is parasitic drag coefficient? You should be able to just say it.
CD naught.
CD naught, yes. So it's 0.02. So the first answer is 0.02. This is CD naught. Then lift when the aircraft is operating at max L by D. Coefficient of lift, CL max, CL at L by D max. CL at L by D max. What is the equation? We've done this so many times now. under root
CD naught by K.
CD naught by K. Correct. So just substitute it and let me know what is the answer. Is equal to 1025, right? So these are the two answers. Yes, 1.03. Okay, so with this, I think we've come to the end. This is all we had in store for today. So does anyone have any questions, or is everyone okay with whatever we've discussed today? Is there any question, any doubts? Okay, if not, we'll end the session here. We'll all meet on Tuesday, and all the very best for your 2 assignment due dates. Both of them are due tomorrow, week 1 and week 2. I think they're both due tomorrow, right? Yeah, so all the very best for those 2 assignments. We'll meet again next Tuesday. Thank you.
And can I ask a different question out of this?
Yeah, sure.
How can we plot the graph of payload versus altitude?
Payload versus altitude. Payload is something that we have, it's part of the design mission requirement, right?
Yes.
So how will we plot it with altitude? It will remain constant, no?
While designing, we can vary the payload for the safety, how much it is. There was a question to identify the graph of payload versus altitude.
Oh, where was this question?
It was not here like that. I was reading something else.
Okay. I'm not sure how we would do that. Maybe you can just, so it would just change the weight, right? So overall, the W takeoff itself would change. Weight of payload would remain constant. So I think if you find a graph that permitted takeoff weight for given altitude, then it should be the same graph. Let me think about it. Maybe put it up on the forum so a lot of people can try to answer this. It's interesting, but there are other parameters, right? It can't be just these two. Weight of payload versus... So can anyone else try to answer this? Weight of payload versus altitude. What would the graph look like? I'm not sure how it would. Anyone else wants to take up this? Okay, let me try looking into this. I'll let you know next week. But meanwhile, all of you also please look into this. Weight of payload versus altitude, the graph for that. And do put it up on the forum.
Yes, sir.
I think it should be payload, weight of payload versus range. There is one graph existing for that.
Okay.
Yeah,
And
there
that is
is also a
payload
graph of
required.
payload versus range, but this was also, if you can just Google it, and the first graph will show you that.
Okay. If first graph shows you that, then let me just check. So that is payload versus range, right? Okay, let me just look into this payload versus altitude. We'll get back to you next week. But meanwhile, all of you also do look into it. Are there any other questions? Okay, if not, we'll meet again on Tuesday. All the very best for your assignments. Thank you for attending the session.
Hello? So, आवाज में तो फोन है क्या? Hello? How right? Hello? पूरा तू क्या फोन ना करो पूरी तरह वाइड आ रही है ना नहीं हेलो हेलो काकड़ी बस रोटी खाई जाया आओ बढ़दा दाम तो नहीं वीडियो कॉल चुको बनू इतना अरे बनू इतना है ठीक है हेलो पूरा वार्डली यार इस मेरे यार ये वो का फोन वगैरह दिया वार्डली का तो आवाज ही नहीं आती क्या है ये काम मैं अपने बना मैं 2 दिन की तरह मैं अपने